Hi, I'm Terry Soul, and this is Programming Chaos, a channel devoted to fun programming projects to help you hone your programming skills. Today's project is the Mandelbrot set, a classic from computer art and graphics. So this is an example of the Mandelbrot set. You can see it's this beautiful, fractal, colorful pattern that we want to be able to produce. And in order to do that, we need to understand the math behind it, because mathematically speaking, this is literally a set. It's a set of numbers with a specific definition, and then some colors added on for fun. Okay, so I'm going to begin not unfortunately with the coding, but with the math behind the coding, how we define the Mandelbrot set. So here we go. The Mandelbrot set formally is defined as the set of complex numbers, which when you apply this recurrence relationship does not diverge, does not head out towards infinity. And so the recurrence relationship is fairly simple. The next value in the series, the I plus 1 value, is whatever the previous value was squared, and add our starting value, our constant value. And so we just reiterate that process over and over again and look at, does it diverge? And so if you want to think about it step by step, Z0 is the complex number C we're interested in, and I'll talk about complex numbers in a minute. Z1 is then that Z0 squared plus our initial number. Z2 is the Z1 squared plus our initial number, and so forth. If we were to do this with, say, real numbers, the process would be fairly straightforward. So imagine we started with a C of 1, so Z0 is 1. Z1 would be 1 squared plus 1, which is 2, so we'd get a 2. 2 squared is 4 plus 1 is 5, so we'd get a 5. And clearly that does head off towards infinity. That would not be part of our set. On the other hand, if we started sort of boringly with 0, we'd get 0. 0 squared plus 0 is still 0. We'd stay at 0. Our number wouldn't diverge. In general, for real numbers, this sort of recurrence relationship is not very interesting. Where it becomes interesting is when we're dealing with complex numbers. So what is a complex number? Well, a complex number has two parts to it. It has a real part and what's called the imaginary part. And the imaginary part is written out this way, just a regular number times the square root of -1. If you think about it, the square root of -1 can't exist. But mathematicians said, we don't care. We're going to pretend it exists and call it I and refer to these as imaginary numbers. Turns out that is super useful, and you can do all sorts of interesting things with imaginary numbers, including the Mandelbrot set. The way that imaginary numbers are often represented is in the complex plane. So we have our complex number C with an A part and a B part, or a real part and an imaginary part. We can now make a plane where the x-axis is the real part and the y-axis is the imaginary part. And so a number like this, a complex number A plus B, the real part is A. So this would be our A. The complex part is B. So I'll put my B here. And then this is the location of that point in the complex plane. If we think in terms of the Mandelbrot set, this is our starting value C, and we apply the recurrence relationship, which gives us a new number. So it jumps somewhere else in the plane, and then it jumps somewhere else in the plane, and it jumps somewhere else in the plane, and it may head off eventually to infinity, in which case it's not part of the set. Or for a different value of C, if we start with some other number, maybe it heads in towards 0, in which case it doesn't diverge and it is part of the set. Or there's other behaviors that you might see. For some starting values, it might oscillate and then it doesn't diverge. Or for other values, it might follow some chaotic pattern around the plane. But basically, we're looking for each point, does it stay constrained or does it go off to infinity? And we color them appropriately. One thing that's going to be useful to know is if we draw a circle with radius 2, any point that gets outside this circle will eventually diverge. So as soon as our point gets outside the circle, we know it's going to diverge. So we don't actually have to loop to infinity to see how long the points go. We just have to ask, does it ever exceed a circle of radius 2, which is going to be our a squared plus b squared to figure out the radius. This is a. This distance is our b for our point. So we're going to look at, is the square root of a squared plus b squared larger or smaller than 2? If it's larger than 2, we know our number will eventually diverge and it's not part of the set. As long as it stays less than 2, we actually don't know what's going to happen. We just have to keep iterating to find out. So that's the idea. Start with a given value, follow it around the plane, and see whether it diverges, with the hint that if it ever gets outside of the circle of radius 2, we know it's going to diverge. And then the last piece that's going to be helpful in terms of writing the code is, how do we calculate z squared? Well, z is a complex number, so it has a real part and an imaginary part. And to square it, we just treat it like a polynomial. So we take our z and we multiply it by itself. And we do this like with a polynomial. So the first thing is we do the a times a term to give us a squared. And then we do the b times b term, and what's interesting there is we get b squared, but I times I, well, I is the square root of -1. If we do the square root of -1 times the square root of -1, we're squaring it, so that gets rid of the square root, and we're just left with a -1. And so that's where this negative comes from. A squared is a real number. bi times bi gives us negative b squared, which is a real number. So this is the real part of z squared. And then we're just treating this as polynomials. So the other term we have to worry about is a times b and another a times b. So that gives us 2 ab's. And from the b, we have the imaginary part in there as well. So this is our imaginary part, 2abi. So z squared is a complex number still, with a real part and an imaginary part. In code, we don't have a complex number type to work with. So in the code, we're going to have to keep track of a and b as 2 separate values. So I'm going to have 2 variables that I'm working with, the a variable and the b variable, and we'll manipulate them in ways like this in order to calculate the new complex number. So with the math out of the way, now we can jump into the coding. So here I have a little boilerplate code to get us started. My setup, I have a window which is fairly small. This is smaller than I usually use, but the issue is calculating the Mandelbrot set is fairly slow. For each pixel in our window, we've got to go through this iterative process to decide, should it be part of the set or not? So I've got to go through a whole loop just to color in 1 pixel. The bigger my window, the more sets of loops I have to go through and the slower the process is. So I'll start with a small window. You, of course, can use a bigger one if you're more patient than I am. For the color mode, I'm just using hue, saturation, and brightness. For the hue, I want to do a full 360 color wheel, and I like saturation and brightness just varying from 0 to 100. And then we're going to be drawing individual pixels, so I don't need a stroke in there. In terms of the draw loop, as I said, what we need to do is go through each pixel and decide whether it's part of the Mandelbrot set or not. So I just need a couple of nested for loops to go through each pixel value. So there we go. There's my nested for loops to go through all of the x and the y values. Now what I want to do is take each xy pixel and send it to a function that I need to write that will determine whether or not that pixel is part of the Mandelbrot set. The only tricky part there is I'm not interested in the Mandelbrot set from 0 to 400 because that's not very interesting. I already said the only interesting area is from -2 to 2, so right around the center. So when I send those values to be calculated, I'm going to rescale them, and I'll type that in and then explain how it works. So here we go. I'm going to get back a color. When I call the Mandelbrot function, which does this calculation for me, I want to pass in the x value, but I'm rescaling x using the map function. And the way that works is originally x is in the range 0 to width. right? So I have a 0 x value all the way up through a width x value. So that's the original range. And I want to rescale it from -2 to 2 because that's the only interesting part of the Mandelbrot set. So I'm just remapping those numbers, and then I'll do the same thing with the y values. There we go. And of course I'm getting an error message because the function doesn't exist yet, but that's fine. So I want to use that color that I get back, which initially will be black or white, depending on whether or not we're part of the set, as my stroke color. And then I'll just fill in that point. And I think I will make this window a little bigger. So now we need to write the function itself. And clearly it's going to take two arguments, the x position and the y position, but I want to think of those as the real part and the imaginary part of my complex number c. We can do that as c sub r for real, or because I was labeling them as having an a part and a b part, this is my constant c, the a part, and this is the b part. And so now the basic thing I'm going to do is just iterate z squared plus c function. So in order to apply that recurrence relationship, I need my z variable. I'm going to create that, and again, it has two parts. It has a real part and an imaginary part, or if you prefer, it has an a part and a b part. I'll stick with a and b. In the initial step, z naught, or z0, is just equal to our constant. So the a part of z is equal to our constant a, and the b part is equal to our constant b. And then I'm going to set this up as a loop to do the recurrence relationship. There are two conditions that keep us inside of the loop. The first one is as long as we're within a radius of 2, because as long as we're within a radius of 2, that we don't know whether or not this number is eventually going to diverge. It could stay within that radius for a while and then diverge, or it could stay in that radius forever. As long as it's within that radius, we want to keep looping. So that is a squared plus b squared, and then normally you would take the square root and compare that to 2. Taking the square root is a little slow, so instead of taking the square root and comparing it to 2, I'll skip the square root and compare it to 4. So as long as that's less than or equal to 4, I want to keep looping. The problem with that is for points in the Mandelbrot set, this will never terminate. By definition, it will loop forever. So instead we say, if it loops for long enough, then we're going to assume it's part of the set. So as long as it's less than 4 and some count, which I have to put in, is less than some maximum value. And I'll put in 500 for now because that tends to work fairly well. And so I need to create that count variable. And certainly one thing I'm going to do is on each iteration, I'm going to add 1 to the count. So I'm not going to loop more than 500 times. Now the next piece we have to do is actually calculate that z squared plus c. And the way I said I was going to do that was like a polynomial in two pieces. So I calculate the za part and the zb part. And so za was going to be equal to the old za times the old za, minus, because we had I squared in there, zb times zb, and then our recurrence relationship was z squared plus our initial constant. So we have to add in the ca part. So it's the real part squared minus the imaginary part squared plus the real part of our initial constant. And if it's helpful, this is the formula that we're calculating over and over again, z squared plus c. So this is the real part of z squared, and this is the real part of c. And then we have to do the same thing for the b part. But here the math was a little different. It was 2 times za times zb, and again, we're adding in the imaginary part of c. This is the way the mathematics works. However, the coding won't work, and you may have already recognized why. Here, when I'm calculating za, I need to use, in a sense, the old value of za, not this new one I just calculated. So if I calculate za here, I'm using the wrong value there. And so the standard thing to do is to store this in a temporary variable. So I'll call this temp ZA, which means I need to create it, of course. And then I can say my ZA should be that temporary value. So now we have our loop. We're calculating our recurrence relationship over and over again. And we're looking to see, does it exceed 4 or does it keep going until we hit 500? And with that in mind, we can now put in our return value. So if we've reached 500, I'm going to assume that we're part of the Mandelbrot set and I want to return the color black. So if the count is 500, I'm going to return the color black. And otherwise, I'm going to return the color white. So again, this hue doesn't matter. I want no saturation, but lots of brightness. So this will give me a whitish gray color. And so once I get that color back up here, we'll set that as the stroke color and we'll draw on the point. And there we go. That is the Mandelbrot set. It's not the colorful, fancy one we were seeing earlier, but this is the mathematical set. All of the black points are ones that don't diverge, at least within 500 loops, and all of the white points are points that do diverge. You can start to see what makes the Mandelbrot set interesting. It's a fractal. It has this basic shape of sort of a big circle with a little circle, but then that is repeated all over at smaller scales. And if we could zoom in, which we do want to add, we could zoom in and see that it repeats at lots of different scales. However, what we don't have is the cool colors, so we should do that. And it turns out that the way the Mandelbrot set is normally colored is based on how many iterations does it take for it to diverge. And so the idea there is to come in and instead of just returning a white color, I want to return a color based on what the count was before we exceeded 4. So I'll take the count. Initially, I'll just divide it by 10 to scale it a little bit, and then times 360 to get our color wheel. So based on what the count value is, we'll pick a different point in the color wheel. And now I do want 100% saturation because I want to see those colors. So there we go. There's the colorful version. And really what this is showing is based on the color, it's how many iterations it takes to exceed 4 or exceed the radius 2 and head off towards infinity. Okay, so the last piece, or almost the last piece I want to put in, is the ability to zoom in and also to move around so that we can sort of focus on different parts of the image. And to do that, we need a variable to control the zoom, or I'll call it the scale, and also where we're centered. So are we centered on the middle? Right now, this is 0, 0, or can we move around and center on different regions and zoom in on different regions? So I'm going to create some variables to keep track of all of that for me. So there's my scale variable, and I'll start at 1.5, which will be a little bit scaled in. And here's the center location, the X part. I'll move that a little bit to the left just because it happens to look good. Although I'll put in some key controls so you can put that wherever you want, and I'll stick with CY as being 0. And now to make this work right, we have to put this into our mapping function. So when we ask for a point to run through our iterative process, we want to start from the center point, and instead of going from -2 to 2, we simply go from minus the scale to the scale. And the same thing over here. And so if I run just this piece, you can see we've shifted over a little bit because of the negative 0.75, and we've zoomed in a little bit because of the scale. And so if you want, you can simply change these numbers to look at any part of the image that you'd like. Much nicer to be able to control that yourself. And so to control that ourselves, I'm going to use the key pressed function, which is built in, and then set up different keys to change the scale and change the center position. So I'll add a little bit of code here. So if you're not familiar with it, key pressed is a built-in function that it gets called in processing whenever a key is pressed. And then we simply look at what the key is and decide how we want things to change. So here's the first of the keys. If the key pressed is I I want to take the scale and multiply it by 0.9, which effectively zooms in. It sort of shrinks the window I'm using. And so we can run this just to test it. There's the Mandelbrot set, and if I press I, and a key here, you have to click on the window to make sure it's the active window. And now if I press I, you can see I'm zooming in. We're getting a little bit of blur because I'm not filling in the background as I go. And so we get a little bit of overlap between each one. But there we go, that's pretty nice. I can't zoom out, I can't move around. I'll have to add a bunch of other keys. So let me put in those other keys right now. And I'll do it with a lot of cutting and pasting. So there we go. I'm using the ASWD keys to move around. And the way that it works is if I press the A key, for example, I want to shift to the left. So I'm going to subtract from the center location. But as I zoom in, if I'm way zoomed in, I want to take a very small step. So the step is proportional to the scale. So that's the idea. And then for each key, I can move in different directions. So here we go. I can zoom in, I can move over, move up, move right, move down. Can't move down because this should be CY. There we go. Now we'll be able to move down. So let me zoom in quite a bit here. Whoops. Make this the active window. And one thing you'll notice as I zoom in, everything becomes all red. And so to fix that, I'm going to change my color scaling a little bit. So by color scaling, I mean I'm going to take this count and instead of dividing it by 10, I'll divide it by the full 500 that I'm counting up to. And then let's put in a background, just so we don't get that blurring effect. So now, because of the color scaling, most of this looks red. But as I zoom in, you can start to see the range of colors. There we go. So we're starting to see the yellows and the oranges, and even in here you can start to see the blues and greens, and bear with me, I'll zoom in quite a bit. There you go. You start to see the fractal pattern, the sense of a self-repeating pattern. As we zoom in, we see not exactly the same thing, but a very similar pattern at different scales. And you can start to see all of those cool, colorful patterns that come from the Mandelbrot set, different regions of it. And by changing the color scaling, you can get different effects as you zoom in or zoom out. And I'm going to zoom in quite a bit, and we'll start to see things break down a little bit here. So notice we're not seeing individual pixels anymore, we're seeing whole blocks. And the reason for that is we've reached the limit of our floating point numbers. We've reached the maximum precision. And so if you want to zoom in further, what we have to do is switch a bunch of our numbers from floating point to doubles. And scale I'm going to leave as a float. So, and then we'll scroll down here and change these to doubles. And we'll get some error messages as we go because we have to change all of them to doubles. And now if we run this, initially it looks the same, but we'll have much more capability to zoom in. So bear with me and I'll show you that. So there you can see we've zoomed in much further than we could when we were only using floats. And I could probably zoom in even further, but this seems like a good place to pause. The other thing you'll notice is the edges are starting to seem a little more rounded than they were when we were zoomed further out. And the reason for that is our count loop stops at 500, which means there are some points that we may be counting as part of the Mandelbrot set that shouldn't be. So some of these black points might take more than 500 iterations to exceed 2 and start to diverge. And so if we set that count value right here, our limit, at a higher limit, then we might get finer detail in the edges. The problem, of course, is it's also going to slow down our program quite a bit because instead of looping only 500 times, we might have to loop 1,000 times or 2,000 times. Depending on your patience, you can say, well, I want a much bigger window or I want a much higher count, but it is going to slow everything down quite a bit. The other thing that you'll notice is now that we've zoomed way in, all of our values are looking red. So we might want to change our shading here based on the scale. So you can play around with using the scale as a factor so that as you zoom in, you get better and better resolution of your color. Okay, so there's a couple of things to play with, and of course, modifying the code yourself is sort of the way to learn and stretch your skills. So don't just program this and stop. Try adding a little more to it. Another nice thing to do is to have it print the values. So print what the scale is, print what the center, the CX and the CY are. Because if they're printed, you can then do things like go in and hard code them initially, maybe blow up your image to full screen size and print it. So if you want to get nice pictures that you can print, you can do this approach with a smaller window to explore until you find numbers that you really like. Then you can draw those full screen and print them or put them on a t-shirt or whatever it is that you want to do. Okay, so some things to play around with. Thank you.